Good morning. Welcome to IEEE SOCC 2022. My name is Dr. G.S. Javed, founder, King Consultants Education. Today's talk will be on noise analysis of CMOS ring oscillator based capacitance measurement for lab on chip application. A quick overview. We will first discuss the introduction and the system architecture. Next, we'll talk about the pixel architecture that is there in this array. What is the oscillator in the pixel? The noise analysis of the oscillator in the pixel, results, and summary. A 3x4 sensor pixel array for lab on chip application was designed in this work. The good sensor dynamic range is expected to have about 100 femtofarad to 300 femtofarad for autofarad resolution of cell health detection. Electrodes, which are physically in the same dimension of the intended cells, are best suited for this application. These cells or these electrodes have typical parasitic value of 50 to 100 femtofarads. The sensor noise floor becomes now the smallest detectable frequency shift. In this noise analysis of this 3x4 pixel, we have built-in process calibration. We have a control pixel to understand the differential measurement. We have 9 active pixels in the blue, and we have a built-in common ADC for the digital readout. Going on into the pixel architecture, here if you zoom in to this active pixel in blue, you would look at the effective design, which is as follows. You have a differential capacitance measurement design where a ring oscillator based capacitance to frequency conversion is done. This has tunable and has high gain aspects. A PFT charge pump based frequency to voltage conversion is used for readout, and the on-chip ADC, which is common to all the pixels, helps in the digital readout of the system. So this is how each pixel is designed. Capacitance measurement design can be explained as follows. The sensitivity of the oscillator depends on the amount of capacitance seen in the load section. Now each of these capacitances would vary the frequency directly or linearly, and this linear relationship of frequency variation due to the capacitance is used here in its differential mode to identify the total differential capacitance measured. The ring oscillator has a set bias depend on which you can tune the sensitivity of the RO. In this case, it is using current dependency, and as you increase the current, the sensitivity of the oscillator increases, albeit the noise also increases with that. So there is a trade-off between what is the best natural frequency and how much of sensitivity can be maintained. Each of these frequencies are enabled at the same time, and when there is no load present, there is a finite FREF and a finite FSense corresponding to each of these oscillators, which are the reference oscillator and the sensing oscillator. When you load the sensing oscillator with the sensing capacitance, the frequency decreases, because as the capacitance increases, the oscillator's frequency reduces. Now this difference in the capacitance can be directly correlated to what is the delta in the capacitance. In this figure, the triangle which represents the center frequency and its phase noise skirt of fsense1 is having the oscillator output without the sensing material. But at the along with the sensing material, the output becomes fsense 2, which directly correlates to delta C2. So the difference between these two frequencies will essentially give the difference between the two capacitance values. So the delta C that you identify between these two is the capacitance measurement. To do a reference to it, one of these oscillators should be fixed or should not vary. Any variation here would give rise to noise, and the noise threshold or the noise reference would come down. Rather, the noise power would actually go up. So in an effort to reduce the noise power, one of the oscillators being the reference oscillator, is stabilized by using injection locking. Either a self-injection locking or a supply-based injection locking can be done to lock this frequency. This way, the capacitance measurement design is explained. Going further, let us look into how the architecture of the oscillator in the pixel is designed. We will place emphasis on two aspects. One, the current bias control, which will control the sensitivity of the system. Second, what is the amount of capacitance loading that you have. This is a ring oscillator, three-stage ring oscillator having equal capacitive loads C1, CS and C2 at each of the inverter nodes, and each of these inverter cells or delay cells is controlled using the bias here. Each of these bias, and this can be controlled either on chip or externally, both tunability is given, and increasing the current increases the amount of frequency, and that increases the sensitivity to the capacitance that is present. So you have a correlation of I versus F versus 1 over C, which brings the correlation in the system. So this is the architecture of the noise of the oscillator in the pixel that we have used. Coming into the what are the sources of noise in the ring oscillator. Now the ring oscillator has got mainly environment noise and oscillator system based noise. So what are the environment based noise that are looking at? First would be the temperature variance or the supply variance VDD. Second would be the ground bounce to find out what. Third being the temperature variance. Now if you pay close attention to this circuit, you would see the out of the three inverters, the first two inverters have their own nominal capacitance CL, and the second the last inverter is modeled with the drains of each connected to the ground by using the current in the thermal noise. Likewise, a current based supply noise is introduced. The capacitive CL load is present, and the sensor front end SFE is modeled as effective R and C along with their own flicker noise component. So these three effectively are taken. The reason why RC equivalent is done because we are not operating at a very high frequency where the impact of inductance it comes into play. So that is the reason it is RC based system is limited here. Another component that you incorporate is the R. So the load in itself has a resistive component, and this resistive component is a noisy component or it is lossy. So this lossy component is modeled as sigma square delta R by R, which is captured here. Now if you look at the table given below, there are 5 noise sources as listed from the figure above in blue listed in this table, and these have been characterized into two environments. One is measuring the environment noise that is external to the design. The other are internal to the design, which would be the thermal noise, which is delta R by R or the resistive lossy component. And there is a differential delay mismatch component which is introduced by the flicker noise, that is sigma square T delta N, introduced because of the sensor and its performance. So this entire phase noise of these oscillators can be correlated as environment related phase noise, psi phi ENV omega, and oscillator phase noise, psi of phi oscillator omega. So these are the components, and these components contribute to the accumulated jitter in the system output. And this accumulated jitter finally takes up what is the range of measurement, and it also tells what is the noise threshold below which measurement may not be easy to happen, and all measurements need to be above it. If you also look, there is a switch based connection where the C pad of the system and the bond wire capacitance of the packaging and the external stray capacitance Cx are also modeled, giving a C effective here. In this case, the Cx maintained is comprising of the sensor capacitance externally used and the board trace capacitance that is brought out. The C effective pad is given as what is the C pad value and the ESD protection present at that load and the switch capacitance that is present. So all these are cumulative. So these will be helping in calibrating the system and getting the effective output done. So this is the environment of the noise measurement and the environment in which the oscillator is doing the measurement. Now let us discuss about the results what was observed. So if you look at the simulated phase noise of the ring oscillator, the noise profile for the various noise models is shown, where the pulse modulation, then there is amplitude modulation, thermal noise, and what is the effective final phase noise is given here in blue. So the cumulative impact of green, red and dark blue curves is given in the final phase noise curve in the light blue. And you can see the free running oscillator has a profile where it starts at almost greater than 0 dBc at 100 Hertz, goes all the while to minus 150 dBc at 100 megahertz. Injection locking now is done to ensure that the noise level of the measurement area, which could be the effective usage, drops, and it allows you to find out what is the difference in the measurement that is present. For example, in this particular case, as a setup for the phase noise measurement, the sensor capacitance is a free running oscillator, and the control capacitance, wherein there is a CREF, which is also called the reference oscillator, is injection locked with the arrow. So in the graph that you see, the blue graph shows the phase noise in the reference oscillator after it is injection locked and versus before the injection locking. If you see, there is a gap from minus 30 to almost minus 75, minus 40 dBc of noise is reduced, and when you translate minus 45 dBc into number of bits or effective number of bits, they quickly translate to about 7.5 bits of resolution gets better. So there is a clear advantage of having injection locking and also ensuring the measurement is enhanced. After the source of noise are there, we find out what are the methods of design for testing and the calibration that is introduced into the system. Since there are many variables that can impact the noise, various switches are present to explain the same. If you look at the C0 where all the switches are off, the effective capacitance that you see is only the parasitic capacitance C par and the pad capacitance C tab for the C sense node. When switch 2 is turned on and all the others are turned off, along with C0 there is a C nominal capacitance which is present. When switch 1 is turned on and all the other switches are turned off, you have the tank sensor C tune, which is containing in the RC tank, turned on to enable the system. When case 3, in which you have the C3 capacitance where S3 switch is turned on and all the other switches are turned off, you have the external sensor which is outside the world being introduced at the system, which carries various other impacts, including the ESD and the trace capacitance mentioned. The four values of capacitance is present when switch 2 and 3 are turned on and switch 1 is turned off, where you have C0 plus C nominal plus C extension external sensor present for all of these. So this effectively tries to leverage the various capacitances that are observed at each of these nodes due to the temperature, due to the ground bounds, due to the supply, and due to the thermal noise seen in the system. This is an enabler, and this elaborate enablement allows us to calibrate as well as measure with utmost noise reduction in the system. For a C norm of 8 picofarad, that means having the C nomination nominal capacitance at 8 picofarad and having a dynamic range of 200 femtofarad in the system, when this capacitance was swept, the total output voltage measurement is shown in the black line. It is fairly linear as the quadratic fitting of that particular line is closely matching with each other. So we are closer to a quadratic fit than to a linear fit. So if you look at the error voltage given, output linearity error, we see that the quadratic value is much constrained to plus minus 0.01, and the linearity error is given by that. And this is obtained after 1 point calibration happening at middle of the dynamic range, that is at around 100 femtofarad. So at 100 femtofarad, the normalization and calibration happens to allow a linear fit, and this shows that there is equal and opposite values of the zero line in the linear and in the quadratic data fitting. So in summary, we have shown a 3x4 pixel array lab on a chip prototype was designed and discussed. The capacitance measurement design was also explained. We went through the sources of noise and the noise analysis in the ring oscillator, where the measurement in the environment and in the system were both highlighted. The use of injection locking and its application in the measurement range and the voltage readout was shown, and an elaborate DFT and calibration scheme was discussed, which helped in achieving an accuracy or output linearity error of plus minus 0.1%. The references are plotted or given in the paper, and they are not listed here as they are too many. With that, I am Dr. G.S. Javed, founder King Consultants Education, thanking you for giving your time to listen to my presentation. I am open to questions right now, and I would like to thank the track chair for allowing me to present my work at IEEESOCC 2022. Thank you. Have a good day.